Okay, we'll get back to section 3.1, and I'm going to try to finish that one off here. So we are talking about the power rule. Also, the derivative of a constant is always 0. Those are the two main things that we've looked at so far. And okay, here's a theorem. It says that if f and g are both differentiable, then the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference in the derivatives. Now remember, differentiable means that you can take a derivative anywhere. Okay, so we don't have any sharp turns, we don't have any vertical tangents, and there's no discontinuities. Those three items all mean that you have you're not differentiable. Okay, if we take a look at proof of item 1, proof of item 2 would be very similar. So the derivative of f of x plus g of x, I need to show that that is the derivative of f of x plus the derivative of g of x. So I'll use the limit definition. Okay, we got the limit as h approaches 0 of the difference quotient. Here's our function, f of x plus g of x. So I need f of x plus h plus g of x plus h, and then minus the function all over h. The next thing I'm going to do here is let's put the functions for the expressions for f together and then the expressions for g together. So I've got f of x plus h minus f of x, and then plus g of x plus h minus g of x. And let me go ahead and split this into two fractions here. And at that point, then I can split this into two limits, right? Limit of a sum is the sum of the limits. So the limit as h approaches 0 of f of x plus h minus f of x all over h, that would be by definition how we define f prime of x. The limit as h approaches 0 of g of x plus h minus g of x all over h, that would be by definition how we define g prime of x. And that's what I had to get to, right? I had to show that the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. Okay, so here's an example. Suppose that we have f of x equals x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x cubed minus 6x plus 5. I want to differentiate that. Well, I can just differentiate each term individually, right? That's what I was just talking about up here. So you're going to use the power rule on all the terms except for the last one. Bring the power down, reduce the power by 1. So the first term is going to be 8x to the 7th, and then plus 12 times 5 is 60, be 60x to the 4th, minus 16x cubed, and then plus 30x squared, minus 6x to the 0 is 1, because it would be a minus 6, and then plus the derivative of 5 would be 0. Okay, and that'd be my answer there. Here's another one. Okay, suppose that we have g of y equals 3y minus 5 squared. Okay, now something that we're going to learn about later on here, which is super important, this is in section 3.4, is called the chain rule. This can be calculated using a chain rule, but we haven't talked about that yet, so I wouldn't want to look at the problem like that at the moment. But sometimes before you differentiate, you'll want to simplify. Okay, so why don't we go ahead and FOIL this out. 3y minus 5 times 3y minus 5 is 9y squared minus 30y plus 25. Then I can just differentiate each term individually. Okay, and so g prime of y would be 18y to the first minus 30 and then plus 0. Here's another example, okay? Now, I've got a quotient. In the next section, we'll talk about the quotient rule. We haven't done that yet, so I wouldn't want to look at doing the problem like that if I haven't talked about it yet. You'll want to simplify first. Let's go ahead and split this single fraction into three terms. The square root of x divided by x squared, that would be x to the negative 3 halves. You're going to keep the base and subtract the powers. 1 half minus 2 is negative 3 halves. The middle term, 2x over x squared, that'd be 2 over x, or 2x to the negative first. And then minus 3 over x squared, the same as minus 3x to the negative second. Now, I'd want to look at this in terms of using exponents here, so then I can use the general power rule. Okay, and I think we're ready to go ahead and compute y prime. So the first term, bring the power down, reduce the power by 1. You're going to have negative 3 halves x to the negative 5 halves, and then minus 2x to the negative second, and then plus 6x to the negative third. By the way, make sure that you're subtracting 1. I see students sometimes on accident add 1 to the exponent. Don't do that. And then let's rewrite this so that we don't have the negative exponents. We're going to have negative 3 divided by 2x to the 5 halves, and then minus 2 over x squared plus 6 over x cubed. And we circled, that'd be the answer. Okay, here's another example. H of u is given there. Now, the square root of 2 times u, we can differentiate that with no problem. The square root of 2u, I'd want to split that into 2 radicals. So it'd be the square root of 2 times the square root of u. And then I'll just leave the last term as is. Okay, so I think we're ready to get the derivative now. The square root of 2 times u would be just the square root of 2. The square root of 2 is just a number, right? So and now the square root of u would be u to the 1/2, which means that I'd want to leave root 2 alone and then differentiate u to the 1/2. That'd be 1/2 u to the negative 1/2. And then the square root of sine of 2, that'd be 0, right? That's just a number. The derivative of a constant is always 0. And so if I rewrite the last term there, 2 divided by 2 times u to the 1/2, or 2 divided by 2 times the square root of u, I can combine the square root of u over the square root of 2 over the square root of u would be the square root of 2 over u. The 1/2 you can leave in front there, and so this would be my answer then. Okay, here's another example. Suppose that we had an equation of the motion of a particle. Suppose that we had this formula S. S is in meters, and t is the time, which is in seconds. Okay, and this models the position of a particle moving. To find the velocity of the object, we take the derivative of the position function. Okay, so I need to find the derivative of s with respect to t, or v of t. Well, power rule on these terms, right? So it's going to be 6t squared minus 14t plus 4, and then derivative of 1 is 0. Okay, now if I wanted to know the acceleration function, that'd be the second derivative of the position function, or you just differentiate the velocity function. Derivative of v with respect to time t. Okay, so let's do that. It's going to be 12t to the first minus 14. Okay. Now let's plug in some numbers here. And by the way, the acceleration is the instantaneous rate of the change of the velocity with respect to time. So how is the velocity changing? You know, is it increasing or is it decreasing? Let's plug in a number. So suppose we want to know what's happening at 3 seconds. The position of this particle, when I plug in 3, I get 4 meters. Okay, now how about the velocity of the particle at 3 seconds? Well, if I plug 3 in to the velocity function, 6 times 9 is 54, and then minus 42 is 14, plus 4 is 16. Meters per second. Make sure that you have the units there, because you're looking at how the position changes over time. The position is in meters, the time is in seconds. Now how about the acceleration at that moment in time? Well, if I plug 3 into this function, 12 times 3 is 36, minus 14 is 22 meters per square second. Now the acceleration is describing how the velocity is changing over time. The velocity is meters per second. This is over time. So meters per second over seconds would be meters per square second, or meters over square seconds. Okay, and again, make sure that you have the units there. Make sure that the correct units are there. That'd be something that I'd be looking for, you know, when I grade these. So now just an observation. The fact that the acceleration at 3 seconds is 22 meters per square second, that means that the velocity is increasing at that moment in time. Okay. If that were a negative, then the velocity would be decreasing at that moment in time. All right, now the last thing I want to do is I want us to investigate the derivative of the exponential function using the limit definition. Okay, and we're going to introduce this. Unfortunately, we're kind of limited in what we know right now, and so there is more to know, and we'll have to get back to a formula for f prime of x later on once we've talked about some more things here. So, but let's just investigate what's going on at the moment. Suppose I have the function f of x equal a to the x, and I want to compute f prime of x. I'll start with the limit definition in terms of h. F of x plus h would be a to the power x plus h minus f of x, that'd be a to the x all over x. A to the x plus h, that'd be the same as a to the x times a to the h, right? I'd keep the base and add the powers there to get to that previous line. And a to the x is in common now to these two terms, so I can factor that out of the numerator. Of course, I can't plug in 0, right, because I can't divide by 0. Now, this function is in terms of h, so anything involving h has to be, stay inside the limit. A to the x does not depend on h, so you can treat that as a constant. Constants can come out of limits. Okay, so now I'm at this point here. Well, since f prime of 0 is the limit as h approaches 0 of a to the h minus 1 over h, where does that come from? Well, here's f prime of x. So if I replace x with 0 right here, a to the 0 is 1. Okay, so I'm left with this limit then, disregarding the a to the x, right? Because I got a to the 0 is 1. Okay, so then a formula for f prime of x would be where you take f prime of 0, which is that limit, and then multiply by a to the x. Okay, in other words, take the exponential function a to the x and then multiply by the slope of the graph at 0. What if we have a being 2? Okay, then let's find the slope of the graph at 0 for y equal 2 to the x. Well, I'm using this formula here, right? And so a is 2. Now, in your book, on page 178, they're describing this same problem here. And so here's where I'm at in the calculation so far. We have f prime of 0 is this limit here. Now, we're just guessing the value of this limit based on this information that we have in this table. We're letting h get closer and closer to 0 just on the right side, and it looks like the y values are approaching 0.69. Okay, and so that's where I'm getting this output here. The value of this limit would be roughly 0.69. Okay, so if we wanted to differentiate y equal 2 to the x, that would be where we take 2 to the x and then multiply by roughly 0.69 using this formula here. Okay, now what if the base is 3? Okay, what if I want to differentiate y equal 3 to the x? Well, it's going to be 3 to the x times the slope of the graph at 0. So I'll need to have an idea of what the slope of the graph at 0 is using this limit. And again, I'm only able to guess the value of this limit. Okay, you guys will actually be able to know the exact value shortly, but there is more to talk about with this stuff here. So again, just getting back to this problem here, if the base is 3, then we've selected some h values getting closer and closer to 0. It looks like the y values are approaching 1.1, you'd guess. Okay. So we would estimate that number as roughly 1.1. All right, so the derivative then of 3 to the x would be 3 to the x times roughly 1.1. Okay, now we're not able to know the exact numbers, okay, because there is more to know with derivatives and logarithms. Okay, there's a connection with logarithms here. We haven't gotten to that yet, so this is really all we can say at the moment about if we want to differentiate y equal a to the x. But we can investigate a little bit further here, okay? Now, 1 is a number that is between 0.69 and 1.1. So I'm going to define the number e to be the number such that the limit as h approaches 0 of e to the h minus 1 over all over h is equal to 1. E, by the way, we already know what that number is, right, from algebra. E is between 2 and 3. So I'm defining this number that is between 2 and 3 to have an output for this limit calculation that is a number 1, which is between 0.69 and 1.1. Now this is one way to define the number e. Throughout the course, and actually moving on into Calc 2 and Calc 3, you're going to see various definitions for the number e. There are lots of different ways that you can describe e. E is a super important number in math, okay? So here's one way that you can define e to the x. The derivative of e to the x would be e to the x times the slope of the graph at 0, which is 1. So the derivative of e to the x is itself e to the x. Y equal e to the x is the only function whose derivative is itself e to the x. Okay. Now let me draw a picture of what's going on here. So geometrically, this means that if you look at all the exponential functions, y equal e to the x is the only one whose tangent line at 0, or what would be 0, 1, has a slope that is exactly 1. Okay, so like here's y equal 2 to the x. Oops. Sorry, it'd be the top curve right here. You're going to pass through 0, 1, and then it'd be this curve right here. Okay, y equal 2 to the x. The bigger the base, the bigger the shot upward, right? So here would be y equal 3 to the x. E is between 2 and 3, so here would be y equal e to the x. Okay, now notice how all three of these curves pass through the point 0, 1. Y equal e to the x would be the only one whose slope of the graph at 0, 1 is exactly 1. Any other exponential, y equal a to the x, is going to have a slope of a graph that is some other number, not exactly 1. Okay, so like with y equal 2 to the x, the slope of the graph at 0 is 0.69, okay, roughly. If for y equal 3 to the x, the slope of the graph at 0 is roughly 1.1, okay. Now those numbers are close to 1, okay, but they're not exactly 1. So y equal e to the x is kind of special in that it's the only function whose slope of the graph is exactly 1 at x equals 0. Okay, and that's one way to define the number e. Okay, there are lots of different other ways that we're going to look at the number e all throughout the course, like I said. All right, now let's suppose we have this function f of x equal e to the x minus 5x, and we want to find the derivative. Well, the derivative of e to the x is itself e to the x. Derivative of negative 5x would be minus 5. If we want to find the second derivative, okay, the derivative of e to the x is itself e to the x. The derivative of a constant is always 0. How about the third derivative? Well, that'd be e to the x. The fourth derivative, that'd be e to the x. So any higher order derivative that you compute after the second derivative would always produce e to the x, right? Because e to the x is itself, the derivative of e to the x is itself e to the x. So, the 100th derivative of f would be e to the x. How about g of x equals e to the x plus 1 plus x to the e? What is the derivative of that? Well, e to the x plus 1, that'd be the same as e times e to the x, right? I'd keep the base and add the powers. E is just a number. The derivative of e to the x is itself e to the x. Okay, and I'm ready to compute the derivative now. Okay, computing g prime of x. So here's that first term, plus the derivative of x to the e. Well, that'd be I'd have to use the power rule, right? I'd have to bring down the power and then reduce the power by 1. I'm going to get e times x to the e minus 1. And e is in common to these two terms. You can factor that out. X to the e minus 1, that'd be the same as x to the e times x to the negative 1. And you can write x to the negative 1 as 1 over x. Okay, so here's what we got in simplified form there. Okay, like I said, we'll be looking at more with derivatives of exponentials, but there is more to know. We need to know the chain rule. We also need to know things with logarithms. So more on that later. Right now we're done with section 3.1, so be sure to look at the homework problems that are on page 120 for me, the odd numbered problems listed.